So here is part 3 of the strength of materials practice final exam. So number 7, hollow circular column has length L equals 3.5 meters, outer diameter 90 millimeters, and inner diameter 70 millimeters. Elastic modulus E equals 205 GPa. Our boundary conditions: fixed at bottom, pinned at top. Part A, derive the effective length factor. Part B, determine the Euler critical load. Part C, determine the radius of gyration. Part D, compute the slenderness ratio. Part E, if an imperfection causes eccentricity equals 2 mm, derive the maximum compressive stress. And Part F, discuss when Euler theory ceases to apply. So column buckling for a fixed pin column, K is about 0.699. Euler critical load, P sub CR, equals pi squared EI over quantity KL squared. Moment of inertia for hollow circular section, I equals pi over 64. And then here we have D outer diameter to the fourth minus D inner diameter to the fourth. I equals pi over 64 times a quantity 0.09 to the fourth minus 0.07 to the fourth. So I is equal to 2.042 times 10 to the negative 6 m to the fourth. Building on that, the area is pi over 4 times the quantity D sub outer diameter squared minus D sub inner diameter squared. So A is equal to pi over 4 times the quantity 0.09 squared minus 0.07 squared. So A is 2.513 times 10 to the negative third m squared. Our critical load here, P sub CR equals pi squared times quantity 205 times 10 to the ninth times 2.042 times 10 to the negative sixth over 0.699 times 3.5 squared. P sub CR is 6.90 times 10 to the fifth n. P sub CR is 690 kN. Radius of gyration, R sub G equals square root of I over A. R sub G equals 0.0285 meters equals 28.5 millimeters. Slenderness ratio, lambda equals KL over R sub G. Lambda equals 0.699 times 3.5 over 0.0285. Lambda equals 85.8. For eccentric loading, secant formula, sigma sub max equals P over A times bracket times, so the bracket 1 plus EC over R sub G squared. And this is the secant of KL over 2RG, R sub G, times the square root of P over EA. And this is where C equals this D outer over 2, and C equals 45 mm. And by Euler theory becomes unreliable when the column is not sufficiently slender, when material yielding occurs before elastic buckling, or when imperfections, eccentricity dominate the response. Okay, number 8. Number 8, we have a thin-walled cylindrical pressure vessel, and it has a radius of R equals 0.6 meters, thickness T equals 8 millimeters, internal pressure P equals 4.2 MPa. Material properties: yield strength, sigma sub y is 280 MPa. Poisson ratio is nu equals 0.29. Part A, derive the hoop stress. Part B, derive the longitudinal stress. Part C, determine principal stresses. Part D, determine strain in circumferential direction. And Part E, evaluate safety factor using von Mises criteria. So this is a pressure vessel and failure theory problem. Hoop stress here, sigma sub h is PR over T. So sigma sub h is 4.2 times 10 to the 6 times 0.6 divided by 0.008. Sigma sub h is 350 MPa. Longitudinal stress, sigma sub L is PR over 2T. So sigma sub L is 315 over T. Sigma sub L is 157.5 MPa. For a thin-walled vessel, sigma sub 1 is equal to sigma sub h. Sigma sub 2 is equal to sigma sub L. Sigma sub 3 is about 0. So sigma sub 1 is 315 MPa, sigma sub 2 is 157.5 MPa, and sigma sub 3 equals 0. For our circumferential strain, that's 1 over E, and then times sigma sub H minus nu sigma sub L, and then we get 315 minus nu times 157.5 over E, so nu is 0.29, so we wind up with 269.3 MPa over E. And for the von Mises stress, sigma sub Vm is the square root of sigma sub H squared plus sigma sub L squared minus sigma sub H sigma sub L. So from here, sigma sub Vm equals square root of 315 squared plus 157.5 squared minus 315 times 157.5. Sigma sub Vm equals 272.8 times MPa. Our safety factor is N equals 280 over 272.8. N equals 1.03. So the vessel is barely below yield by von Mises theory. And moving along now to number 9. Cantilever beam of length L carries N force P and distributed load W of X equals W naught X over L, which varies linearly from 0 at the wall to W naught at the free end. Part A, derive the strain energy due to bending. Part B, use Castigliano's theorem to derive tip deflection. Part C, compare the result with direct integration. Part D, determine equivalent spring constant of the beam. So this is an energy method cantilever problem. Use Castigliano, introduced a dummy N load at the free end. The bending moment at the section X is M of X equals Q times L minus X plus the integral from X to L, W of S minus X ds. So M of X equals Q times L minus X plus integral from X to L, W naught S over L, S minus X ds. So M sub W of X equals W naught over L times the integral X to L quantity S squared minus XS ds. So M sub W of X equals W naught over L times a quantity here S cubed over 3 minus XS squared over 2. L and X and L are bounds after integrating there, and then substituting M sub W of X equals W naught over L times the quantity L cubed over 3 minus XL squared over 2 plus X cubed over 6. So we're going to wind up here with M of X equals Q times L minus X plus W naught over L, bracket L cubed over 3 minus XL squared over 2 plus XL plus X cubed over 6, close bracket. So building on that, the strain energy, we get U equals integral from 0 to L M of X squared over 2EI dx. Tip deflection due to the distributed load is going to be delta equals that partial U respect to Q, Q equals 0. So this delta is going to be the integral from 0 to L mw of X L minus X over EI dx. Carrying out this integral, performing the operations, delta equals 11 W naught L to the fourth over 120 EI. If there's an actual N load P, its deflection contribution is delta P equals PL cubed over 3EI. And the total tip deflection is going to be PL cubed over 3EI plus 11 W naught L to the fourth over 120 EI. Equivalent spring constant for the end load component is going to be K equals P over delta sub P, and K equals 3EI over L cubed. And for the combined loading case and effective load dependent stiffness would be K sub EFF equals P over the quantity. This is PL cubed over 3EI plus 11 W naught L to the fourth over 120 EI. Okay, so that's part 3, and that's all for this practice exam in strength of materials. Thank you very much and have a great day.